you want.
Yeah. So welcome everybody. Today welcome Eugenio E.Landi from Pennsylvania State University as speaker of our seminar. He should speak on the topological half of the Grothendieck-Hirzebruch-Riemann-Roch theorem. Yes, please.
Thank you. Thank you for the invitation. And yes, this is the title of my talk, the topological half of the Grothendieck-Hirzebruch-Riemann-Roch theorem. And I just want to say that this is joint work with Mattia Coloma and Domenico Fiorenza. So I can erase this nice title, which I wrote yesterday. And begin with the classical theorem, and I will just talk about the Hirzebruch-Riemann-Roch theorem for a bit. So we know classically that we have a map which is the third character, and I will take it to go from the complex K theory of a space X, which I tensor with Q, to the periodic cohomology of the space X with Q coefficients, and this I will call HP of X. And well, we know this is a classical statement that this map is an isomorphism. Now, a feature that these two cohomology theories share is that they are complex oriented. And for what I care about, this means that if I have X, a complex manifold, let me say, I know that this convention will be hated by most of you, but the dimension of the manifold X will be small x for me. And well, if I have this manifold, I can define these two maps. The push forward in K theory to the point, which is something that goes from Ku in degree x of x tensored with Q to Ku in degree 0 of the point tensored with Q. And this is just the rational numbers. And I can do the same thing with periodic cohomology. So I can define pi star HP, which I also call the integral because it is the actual integral. And this will go from HP x of x to I don't know. And I go to the periodic cohomology of the point, which is again Q. Now I could, in theory, hope that composing these maps in the only obvious way would give me a commutative diagram so that I could get something like this. Ku of x tensor Q goes with the third character to HP of x, and then that going to Q using the push forward here, the push forward to the point here, and the integral here would give me a commutative diagram. Now this is known to be false, since here I need to add a correction factor, which is the top class. In particular, what the correct identity is not this, but is this. Pi star Ku of, let me say, V, which is a vector bundle since it is an element in K theory. This will be the integral of shared character of V times third class of X. And this is what we call the topological half of the Grothendieck-Hirzebruch-Riemann-Roch theorem. And this is what I will focus on. The other half, the algebraic geometric part, is the one that states that the Euler characteristic of a holomorphic vector bundle V is exactly that push forward. Okay. Of V. And this part here cannot be reached using just topological arguments. It is an actual theorem in complex geometry. But I will never care about this fact. I will only care about the fact that I have this three maps that should, in theory, or could, in theory, be part of commutative diagram, but they do not. They need this correction factor here, and the aim of the paper and of the talk is to show that this correction factor is to be expected. Now, the full title of the paper talks about the fancy language of spectra, and so it is only fair that I say 2 words about spectra, and I will not really define the category of spectra. I will not say much about them. I will just list the key properties that I will need. So we have this category of spectra, which, first of all, is not a category, it is an infinity one category, and it has these properties. It is a stable category, and for an infinity one category, this means that it has a zero object, the point, and whenever I have a pullback square, then it is a push out square. Obviously, a homotopy pullback is a homotopy push out. So these 2 features here also give me the fact that I have a shift, since I can consider the fibers and the cofibers of the terminal and initial map and get this, which of course I will never recall the correct shift, but this is it. So if I have my spectrum X, then the fiber of the initial map from the zero object is the object shifted by -1, and of course I have also this, that the cofiber of the terminal map is the object shifted by 1, and this will reproduce what in the category of topological spaces are the loop space and the suspension. Only here, this shift, and so all the shifts for any n are self-equivalences of the category, while in the category of topological spaces, this is not true. Using this fact,
may I ask you, do you work in coherent sheaves, or you work with coherent sheaves? Because you mentioned the abelian the category that is abelian. So you work with coherent, or maybe
no, it's not coherent sheaves. It's category of spectra. It's just the stabilization of topological spaces, if you want.
But you suppose that you work for abelian category, yeah, in abelian category, and for this you make the spectra inside of this.
I'm not really working in abelian categories. I'm just considering it from a homotopy theory point of view.
Mhm.
But I have some, well, I mean,
Because there are problems with homology. There can be problems with homologies, yeah, but what is a co-kernel, whether it exists, and so on, yeah. So you probably.
I didn't catch the question, sorry.
So your homologies are defined by co-kernels, yeah. And these objects must exist, but by.
Yes, these are shifts at the moment. Not, I won't really talk about homologies. Just
Yeah.
cohomologies represented by spectra.
Okay.
I mean, I won't really touch the analogy between stable categories and abelian categories, which is a bit. But yes, there is a strong analogy.
Okay. Yeah, thanks.
I mean, the fact, which I am not an expert about, but yes, the correct analog in the setting on infinity categories of an abelian category is a stable category, which, of course, this thing here reproduces.
Now you are certainly in the realms of, it is correct, I guess, yeah. So I think that you are in the framework which is covered, yeah, by. You don't need to consider quasi-coherent sheaves on manifolds and so on.
Yes, no, I do not. I just care about these are, well, a spectrum in the setting is just a sequence of topological spaces with some property, but nothing else.
Yeah,
then,
thank
of
you.
course,
Sorry for the interruption. I was just somehow curious.
Okay, great. Then this is an infinity category, so I can consider its homotopy category. And here is something which is interesting. The homotopy category HSP is a category enriched in abelian groups. And I will denote the Hom set in the homotopy category with the bracket X. Why? This is an abelian group, and of course, everything works naturally. And you can prove this using, well, the property that the category is stable, and the fact that this Hom set here is, well, it is the pi zero of the Hom space between the two spectra, but actually, since it is stable, it is also the pi 2 of some other spaces, and so it is an abelian group. Now, another property which I will need is that this category here is a closed monoidal category, and of course, it is a closed symmetric monoidal category. And this means that I have a tensor product, which I will call the smash, since it reproduces the smash of base spaces. I have an internal Hom functor, which I will denote by F. And of course, I have a unit, which I will denote with this bold S, since it is what we call the sphere spectrum. And these two objects have the classical adjunction, which I can probably write here, which is that the maps from X smash Y to Z are like the maps from X to the internal Hom. And we will use this fact later. And then last property, which I'm afraid I need to erase a bit of the blackboard to write down, is that we have some important functors from the category of topological spaces to the category of spectra. But let me just say that for what we need, well, we will need everything, of course, otherwise I wouldn't have spoken about this stuff, but we will need shifts and the fact that shifts are self-equivalence, the fact that the Ohm sets in the homotopy category are abelian groups, and this closed monoidal structure here. Now the last property, which I think is property number 5, is that we have, let's take the infinity one category of topological spaces. Then we can take a functor from here to the infinity one category of base spaces, which is just the functor that adjoins a disjoint base point. And here we have a functor which we denote by sigma infinity, which is the suspension spectrum functor, or the infinite suspension. And well, as I told you earlier, a spectrum is some kind of sequence of topological spaces. And if I have a base space here, then it is the sequence, this functor here sends this space X to the sequence X, suspension of X, double suspension of X, and so on. Now, if I take a space here, X, it is sent to X plus here, and it is sent to sigma infinity plus X. This, well, both functors, both plus and sigma infinity, are monoidal functors. They actually respect the monoidal product in all the categories that we have. And this is really important because, first of all, if we take the unit of the tensor product here, which is just the points, since the tensor product here is the Cartesian product, it is sent to S0, the space with 2 points, one of which is marked. And here it is sent to the sphere spectrum, which, of course, you can now understand why it is called like this, because the suspension of S0 is S1, the suspension of S1 is S2, and so on. Now, this fact here, the fact that we have this monoidal functor, is really interesting because we have a nice property of Cartesian categories. So categories where the monoidal product is the Cartesian product, which is the fact that all the objects in such a category are comonoids. So X in top, X is comonoid. And this simply means that we have the diagonal map delta from X to X cross X, and we have the terminal map from X to the point. This is not really true in general. For a general monoidal category, I do not have a diagonal map and I do not have a map to the unit. Now, the fact that this functor here is monoidal means that suspension spectra, so the spectra in the image of the infinite suspension functor, are comonoids in the category of spectra. So again, X in top, this means that infinite suspension plus of X is a comonoid. And this will be fundamental in everything that we will see later. Now, of course, all the spectra which we can get from spaces are comonoids, but we also care about monoids in life in general. And most of all, we care about commutative monoids. So we have a very simple definition. E, a spectrum, is a ring spectrum if it is a monoid spectrum, and it is what we call an E-infinity ring if it is a commutative monoid. And here infinity refers to the infinity opera, since we are working in an infinity category setting. So commutativity has to be considered up to infinite coherent homotopies, but we will not really care about that. Just a couple of facts about E-infinity ring spectra, and from now on, whenever I write down a spectrum which I call E, it will always be an E-infinity ring spectrum. We have some properties. One which is really sensible, it is the fact that I can take shifts in my category of spectra. And well, if I take a ring and I shift it, then it is an E module. This means that I have maps from E shifted by n smash E to E shifted by n, and everything works as expected. 2, if X is a space, I can define the cohomology of my space X as E bullet of X equals the direct sum for n in Z. Now I need to get the correct shift. It is this direct sum of sets in the category, in the homotopy category. Now this object here, if X is a space and E is an infinity ring, is roughly speaking the set of maps from a comonoid to a monoid, and thus it is a monoid in the category where the Hom set live, and so it is a graded commutative ring. And we will use this fact a lot. And third property here, which is really a property of cohomology, is the fact that I have what we call the suspension isomorphism. So once I define this cohomology, the cohomology of a space X is isomorphic naturally with an isomorphism sigma. This blackboard is a bit small, I'm sorry about that. To the cohomology shifted of degree by n of the n suspension of my space X. And I have these isomorphisms for all the integers n. And this too is a fact that we will use a lot, because all the isomorphisms that we will see are generalization of this. So this was very quick, hopefully not too quick, introduction to spectra and to cohomology. Now we will briefly talk about a different category, which will be just as important in this work, which is the category of vector bundles. I will call this category BB. I will not use this too much, but it will be important. And well, the objects of my category BB will be vector bundles, V to X, real vector bundles, and morphisms. A morphism from V over X to W over Y will be a commutative square V W Y X with a map F downstairs, a map F prime upstairs, which is fiber-wise linear. And the nice fact about this category is that I can define here a monoidal product. And I have this tensor, which I define like this. V to X, tensor W to Y is V box W goes to X plus Y. And the box product, the box sum is just is obtained by considering the two projections of X cross Y to X and Y respectively, taking the pullback of V along the projection to X and of W along the projection to Y. So I now get these two vector bundles over the cross product, and I can just take the direct sum of these two bundles. And this this functor here is well, it is associated with monoidal product, so it is an actual monoidal product. And well, we care about monoidal functors today, and this is why I will now give you a monoidal functor from this category to the category of spaces. But before that, I will just tell you that the unit of this tensor product is the trivial rank 0 bundle over the point. So it's just, well, the point goes to the point, but one point I would call R0 for obvious reasons. Now, the monoidal functor which I care about is what is classically known as the Thom space of a vector bundle. So I define this functor EH, which is just the homotopy push out of this. This is one definition. Other useful definitions of the Thom space, which of course agree with this, are, well, for when X is a compact space and V has rank at least 1, which is not a lot to ask, then it is just the one-point compactification of the total space V. If X is not compact, then I have to one-point compactify all the fibers and then quotient by all the points that I've added, 1 point compactifying my fibers. So I am 1 point compactifying, but just in the fiber direction, not in the X direction in some sense. And if V has rank 0, then the Thom space is just the functor that adds a disjoint point. I notice that here it's pretty easy to see, but also in the other definitions, that the Thom space has a natural base point, which is given by this map here. Now, this functor Thom is a monoidal functor from BB top star. And I have another monoidal functor from top star to spectra, which is the infinite suspension. If I compose these two functors, I get a functor from BB to spectra, which sends V to X to X to the V. This is just notation. Thing which is pretty important here is that if V is the trivial rank n bundle, so let me just write it like this. It should actually be Rn cross x to x, but it's just a slight abuse of notation. Then it goes to x Rn, but this is just the infinite suspension of x shifted by n. Now, the reason why we care about this additional monadal functor is that if I have a vector bundle V over X, then the Thom spectrum, oh, well, this is important. This object here is called the Thom spectrum of the vector bundle V. And the Thom spectrum of V is a comodule over the comonoid X. So V is cohomology. And this is really important because the cohomology of the Thom spectrum will now be a module over the cohomology ring of X. A bullet of XV is an E bullet of X. Module. This will be something that we will use repeatedly up until the end of the seminar. Just a quick word about this fact. Here, I only considered actual vector bundles. And one thing that we will need is that we also want to be able to consider virtual vector bundles, so formal differences of vector bundles. And the good news is that we can do that.
Sorry, Eugenio, can I ask
Yes.
a question?
Yes.
So, of course, in geometry, it's a classical fact that sections of a vector bundle are a module over the functions over the base, right?
Yeah.
So this this statement that you made about E dot module E dot of xv being a module of E dot of x, is that some kind of cohomological analog of that? And would you be able to state some analogous something analogous, just you know, referring to the RAM cohomology and some cohomological objects derived from the vector bundle?
I don't really think it is an analog of that.
Ah.
Yes, it is. Yes, I don't think so, because what we will care about in a moment is that sometimes these two objects will be isomorphic. And well, at that point, it will become a bit different, but it may be that I am wrong when I say this, but I don't think that that it is that fact that this is generalizing. But I have to admit, I've never really thought about this in this way.
Okay, all right, just curious. Okay, thank you.
Yeah, but it is an interesting question. Thank you. Yes, it can be actually. I was talking about virtual bundles, and let me just say that I can suppose that I have this formal difference, V is V0 minus V1 over X, of course. Then I can always find a vector bundle which I call V1 prime, such that V1 prime plus V1 equals Rn for some n. And then, of course, this would also mean that V1 prime minus Rn equals minus V1. But now I pass from having minus a generic vector bundle to having minus Rn, which is a bit more manageable. In fact, I can define xv, the Thom spectrum of my virtual vector bundle v, to be x of v0 plus v1 prime, simply shifted by negative n, since I told you that the Thom spectrum of a trivial vector bundle is just the suspension of the spectrum obtained from X. And then I can actually consider the Thom spectrum of minus Rn just by shifting by negative n. And the nice fact is that xv for the virtual vector bundle is still a cohomodule over the suspension spectrum of X. And so a bullet of xv is an e-bullet of X module. Now, a very classical fact about Thom spaces and Thom spectra, actually this is the framework which I prefer, is that we can obtain this Thom space in a quite geometric way. So if we have now X, which is a smooth manifold, and we consider an embedding of X into Sn, then of course this embedding here has a normal bundle nu, such that nu plus the tangent bundle of X is Rn. Now it is a known fact that I can consider a tubular neighborhood of nu, of this embedding here, which is now a space isomorphic to the total space of nu, and I have this nice map here. I can take the map from Sn to, let me abuse a bit more notation and say that my tubular neighborhood of X is called nu. So I can consider Sn goes to Sn quotiented by Sn minus nu. And this space here is isomorphic to the Thom space of my vector bundle nu over X. So from considering this embedding here, I have obtained a map from Sn to the Thom space of nu. This map is a collapse map, and it is called the Pontryagin-Thom collapse map, which I will denote by gamma. A nice feature of this, which we will use, is the following. We have this property here, and let me take the infinite suspension of this map. So I have gamma, which now goes from the sphere spectrum shifted by n to X nu. Now, if I shift everything by negative n here, I obtain a map from S to X nu shifted by negative n. But by this property here, I know that this spectrum here is just X to the minus dx. And this map here is a map which I will call, again, gamma, but it will be the Pontryagin-Thom collapse map that we care about. And another really nice thing is, well, first of all, here now n does not appear anywhere. So here we have to choose in which Sn to embed our manifold X, but here that choice disappeared. So we have this map, and we have another map which will be slightly more general, but it will allow us to state an interesting theorem. I told you that the category of spectra has an internal hom, and I will define d of x to be f of infinite suspension of x to s. Of course, I defined it for a space, but I could define it for any spectrum. Now, when x is a space, x has a map to the sphere spectrum, since we know that it is a comonoid, and so it has the map to the sphere spectrum, it has a map to the unit. And this means that since this functor here is clearly contravariant, we have a map from S to the x. This spectrum dx here is what we call the Alexander-Spanier spectrum of x, because it will reproduce Alexander-Spanier duality. Now, the interesting theorem is the theorem of Atiyah, from 1961, that states that if x is a manifold, a smooth compact manifold, then these two maps are the same. And this means that we have an isomorphism of spectra under S. And this is really interesting, because this also means that we can, well, d of x doesn't actually have to know anything about the manifold structure of the space X, but it has this isomorphism. So that is cool in its own right. But we will use this fact to give, finally, the definition of orientability of a manifold S. We have to fix a ring spectrum E. X is a smooth, compact x-dimensional manifold. Then we say that X is E-orientable if we have this isomorphism here. Sigma from the cohomology of X to the cohomology of X shifted in degree by negative X of the X. And this is an isomorphism. And notice that, well, we say that X is E-orientable if these two objects are isomorphic, and an E-orientation is the choice of the isomorphism, as expected. And the isomorphism, of course, has to be the only kind of isomorphism that we can hope for, and that is an isomorphism of E of X module. This will finally allow us to consider integrals, since we can define integral x sigma E to be a map going from the cohomology of X to the cohomology of dx using sigma, and then to the cohomology of the sphere spectrum. And well, the cohomology of the sphere spectrum is what we call the coefficient ring of a cohomology theory. In particular, if E is the spectrum representing singular cohomology, let's say with rational coefficients, then this map here actually reproduces integration. And E orientability in this case would exactly mean that the manifold X is orientable in the classical sense. So yeah, the tangent bundle admits a reduction to S cohen. So we can consider integrals, and notice that we have the correct shift of dimension. Now we are not happy with just the ability of considering these kind of integrals. We want something more. And that something more is that we want to be able to say that a general vector bundle may be E-orientable, not just the tangent bundle, or say better, the negative tangent bundle, since we have that isomorphism. So we have this easy definition. V2x is E-orientable if we have an isomorphism sigma b from E of x to, you get it, E bullet plus R of xb, where R is the rank of B. Notice that we had E minus the dimension of X earlier, but that was just because minus dimension of X is the rank of the negative tangent bundle. So it is always bullet plus rank, just earlier the rank was negative. Something to, of course, I will repeat it, this isomorphism is an isomorphism of EX modules. Something interesting here is that we may have two different E orientations for the same vector bundle. And this would mean two different isomorphisms. Something like this. Let me say that this is sigma. This is sigma prime. And these two are isomorphisms. And the nice fact is that this diagram will commute if we multiply by an element MV, which is an invertible element in EV. This is just a way of saying, if I have two isomorphisms from E of x to something isomorphic to E of x, then upstairs, I just need an isomorphism, well, an automorphism of E of x as an E of x module, and that is just multiplying by an invertible element. This element here will be what we will later see to be the Todd class in the classical statement of the theorem. So if we have a vector bundle with more than one orientation, we have that invertible element that depends on the bundle and on the two orientations. Now we don't care about just one vector bundle, but about families of them, where I give a definition of what I mean by family. I say that F is closed family of vector bundles, and this just means a set, a proper class, a collection of bundles over generic spaces. And it is closed if whenever I have two bundles in the family, then their tensor product is in F. This is just, well, the tensor product of two bundles in F is in F, and 2, if I have a map F from X to Y, and a vector bundle B to Y, which is in F, then the pullback along F of W is in F. So nothing crazy. This collection is closed under tensor products and pullbacks. And I say that it is stable if it is closed, and 3, it contains the trivial bundles over the point, which means that it contains all the trivial bundles over any space, because we have property 2. And property 4, if I have a short exact sequence of vector bundles over the same space, and 2 of them are in F, then all 3 of them are in F. This will imply that whenever I have 2 bundles in F, then their difference is in F. Their virtual difference is in F. Examples of stable families are plentiful. All the bundles form a stable family. The oriented bundles form a stable family, and spin, string, all the bundles in the weighted tower of ON form a stable family. And of course, framed bundles form a stable family. Complex bundles only form a closed family, since we do not have odd rank complex bundles, and this will mean that we cannot satisfy this property for all n. A nice thing is that whenever we have a closed family, we can stabilize it, and doing that give you stably complex bundles. Now we can orient not just manifolds or individual bundles, but families. How am I doing on time? Okay. So F, a stable family. E, an E-infinity ring. Then we say that F is E-oriented if for all vector bundles in F, the bundles are oriented, so we have sigma B from a bullet of X to a bullet plus R of XB. And I don't think I have time to write the properties that these orientations have to satisfy, but let me just say that they have to satisfy the sensible properties that one may expect. So if I have a tensor product of 2 vector bundles, the orientation of the tensor product is in some really reasonable sense the tensor product of the 2 orientations. And if I have a pullback, the pullback of the orientation is the orientation of the pullback. And something that I really care about is the third property, and it is that whenever V is the trivial bundle, if I have this bundle here, then I want sigma to be the suspension isomorphism. Sigma is, which of course it's nothing weird to us. The sigma should be an isomorphism from the cohomology of X to the cohomology of the suspension of X. And well, I want that isomorphism to be exactly the suspension isomorphism. In fact, all these isomorphisms that we define, the Tom isomorphism is the standard name, are some kind of generalization of the suspension isomorphism.
Eugenio, so
Yeah.
the concept of the orientation here is like in the statement complex vector bundle, or you can have the more example, how to say, better treatment, because that is nothing else like a fundamental class, right? Orientation is the same like a fundamental class. Can I think so?
Yes. Well, the one of the most classical settings is the one of complex orientations, which is the example which I started with. And in that case, things are way easier or more complicated, depending on the point of view, because you can do more computations. But yes, in general, an orientation here, I just defined it as these isomorphisms. In a more general setting, well, in the same setting, but a different point of view, is that an orientation you can see as a map of spectra from a spectrum which is the Tom spectrum of the tangential structure, and in this case, the Tom spectrum of the family F, which is something that one can define putting together Tom spectra of the vector bundles in F. And a map from that spectrum to, in this case, the spectrum E, will give you an E orientation of the family F. Using that, you can actually define characteristic classes. In particular, a complex orientation will exactly be a way of saying this cohomology theory has a theory of Chern classes.
Yes.
So yes, it is exactly that, but I am just focusing on the isomorphism since I just want the push forwards, but of course the theory is much richer than that.
Okay, thank you.
Thank you. So we have this definition of an orientation for a family of vector bundles. And another last word about this, the fact that the suspension isomorphism, the Tom isomorphism from trivial bundles is the suspension isomorphism, can also be seen in, well, from another point of view, of saying that, and this is just heuristics, I mean, it can be formalized, but I will not go into that, that the cohomology theory cannot distinguish the bundles in the family F from the trivial bundles. And so it, some way, thinks that those bundles are trivial, and so that the Tom space of those bundles are just suspension. And so you have that isomorphisms. So the theory kind of refuses that. Now, let's say that we have finally a map between two smooth manifolds. F goes from F, well, from X Y. I say that, and we have family F stable oriented. Then I say that F small f is E oriented if negative TF, which is just F star of Ty minus Tx, is in F. Is oriented if negative tangent bundle is in F. Now, something important is that if the map is the terminal map, so if F is the map to the point, then this definition here just states that negative tangent bundle of X is in F. And so that is exactly the definition of an orientation of X. And second thing, if I have a map F between two oriented manifolds, so such that the terminal maps are oriented, then by the 2 out of 3 property, the property that I told you about, the short exact sequences, then automatically this vector bundle here will be will be oriented. And this reproduces the fact that any smooth map, if you want, between two classically oriented manifolds is an oriented map, and you can consider pushforwards along those kind of maps. Now we can define pushforwards along oriented maps in, well, two different ways, which of course have to agree. The first one is if X and Y are themselves oriented. Then we have isomorphisms between the cohomology of X and that of dx. So we can do this, the bullet of X to the bullet minus X of dx. Then, of course, dx is a contravariant factor, so now we have this map to the y, and we go to E bullet minus X plus Y of Y. This is sigma. This is the F star, and this is sigma. And so we obtain our F star from the cohomology of X to the cohomology of Y, shifted by the difference of dimension. But if the manifolds themselves are not oriented, then we have to do some more work, which I will not do here, but it's basically the fact that we can define a generalization of the Contryagin-Thom collapse map and get a map F from phi, from Y to X minus, well, from the suspension spectrum of this. And this means that I can now define F star as something that goes from the cohomology of X to, using the fact that this that F is oriented, to the cohomology of E bullet minus X plus Y of X minus df, to the cohomology using star of Y. And so if I have an oriented map, I can finally consider pushforwards along all the maps. Now we are almost there, finally. And we can see what happens if a family F has two orientations. Which I will call sigma A and sigma B. Then, well, for a vector bundle B to X, which is in F, I will have something like this. The bullet of X goes using sigma A to E bullet of, well, E bullet plus R of X B. I can do the same using sigma B, and here I will have my multiplication by MV, the correction factor that I had earlier. Now, if I am in the conditions where I have F from X to Y such that negative PF is in F, then I can write down this diagram, which is the first version of the theorem, the bullet of X, and negative PF here, another E bullet of X, then I have X minus X plus Y of this, and this is sigma B, this is sigma A, and down here I have a bullet minus x plus y of y, and this map here is the map phi star from from y to the Thom spectrum of x. Now, the integrals, the push forwards along the map F are exactly these two compositions. And this means that if I take an element A here, I have that F bullet A of A is F bullet B of A times M negative PF. And this is first version. The second version, and this is the last Blackboard that I will write, is this one. And it is the case where I have a map of spectra. So I have psi from E to F, a map of E infinity spectra. And it is a map of rings, actually. It's not just a map of spectra between infinity rings. That is important. And I have a stable family F, and F has an E orientation and an F orientation. So I have F, that. I have sigma E, an E orientation, and sigma F, an F orientation. And I will use the E orientation to define a new orientation on F. Let me just write down phi star sigma E F orientation. Again, as always, I have map F from X, Y, that negative, is in F. So I can write this last diagram, which is the bullet of X. I can take the push forward using the E orientation of F. So it goes to E bullet minus X plus Y of Y. And I will call this F star sigma E. Then here I can go to F bullet minus X plus Y of Y using psi star. This is just a map of spectra, so it induces maps here. And I can do the same thing here, going to to F bullet of X. Then I have a way of pushing forwards my ability of considering push forwards, which just means that I can consider F star psi star of sigma E here. This just means that the push forward here that I choose is given by considering push forwards here and then applying psi to them. But I also have my original way sigma F of considering push forwards. And so this means that I now have two orientations on F, and here I will have M negative PF. This is the diagram, the famous diagram of Grothendieck with the two devils, because I can now rewrite this this diagram here as, again, I have an element A, which is here. I have psi star of f star sigma e of a. I don't have a lot of space, so we'll write here equals f star sigma f of psi star of a times m negative f. And this is exactly the Grothendieck-Hirzebruch-Riemann-Roch theorem. In particular, you recover the classical statement of the theorem if psi, well, if E becomes K-theory, complex K-theory, F becomes periodic cohomology, and psi is the Chern character. At that point, F, the family F, is the family of complex vector bundles, and here, and of course, now this multiplier here M becomes the Todd class of the tangent bundle of F. In particular, if F from X to Y is the terminal map, you just recover that the integral of a Chern of something times the Todd class is just the push forward of, well, here it is the Chern character of the push forward, but the Chern character at the level of K theory and cohomology of the point is just the identity. So this disappears and you recover the initial statement. And well, this is all. Thank you.
So thank you very much, Eugenio, for your beautiful lecture. Yes, that's very nice. There are some more questions. Peter, do you have some comment? Peter, oh, Peter is okay. Peter check lab. Maybe he has something. So Peter is an expert on some spectra. So Peter some back, but he had to left because he have a bit, how to say, longer than usual. So I already asked you from the beginning, but maybe that's you didn't know read the lecture now by Clausen and Peterson. They also consider push forward map, but using how to say category of the perfect complex. And they say that's a natural category for push forward mapping. Yes, so you didn't notice they did not see the paper.
No, I did not. I think that there are some differences in that we just care about the topological picture.
Yeah.
And well, there is a lot to say in the more analytic and algebraic geometric point of view, which we completely disregarded. Because the thing here is that this correction factor appears just because you have that isomorphism of modules, nothing else. If you have two isomorphic rank 1 modules, then of course the isomorphism has to be multiplication by an invertible element. And this is what we wanted to talk about. And then in the paper, we have half the paper which focuses on the complex point of view, which means that we actually do some work to prove that this correction factor is actually the Todd class.
Yes, so yes, these are completely topological one, and you think that's a Clausen and Peterson working on algebraic, complex geometry, yes, more analytic, yes. Yes.
When we talk about complex bundles, we just means bundles which have
topological one.
Yes, exactly, and complex structures on the fibers, but no holomorphicity. So there is a bit of difference there. So yeah.
Yes. If there are no more questions, let us thank the speaker again. Yeah.